last time we were talking about general linear iterative schemes, and today we want to go into one of the basic ways that we can analyze these methods. So this isn't the only method that we're going to be using in this course. In fact, it's not even the preferred method that we're going to use in this course. The preferred method is going to be using something called the energy approach, and it's more modern and useful for the sort of things we want to do. But it's good to know this sort of old-fashioned theory as well. So the old-fashioned theory is what is called the spectral convergence theory. So I need a couple of definitions to get through this, and a lot of you who took 571 numerical analysis 1 with me will recognize a lot of these terms are the same that we use there. It's just keep in mind that we're going to use some of the conventions that are used in multigrid methods, and so some of the definitions change slightly. So let's discuss what we mean by a convergent matrix. This will be a useful topic. Not quite as useful as I thought when I put it in, but somewhat useful. So a matrix C that's square is called convergent if and only if for every epsilon greater than 0, there exists a capital K, such that if little k is bigger than capital K, then for all I and j between 1 and n, in absolute value, the element of the matrix CK, the ijth element, in absolute value is less than epsilon. So let me explain a couple of pieces of notation here. The first one is, in this case, CK doesn't mean, well, it's kind of doing double duty. It's not really like the index for an iteration or a sequence, but on the other hand, it kind of is as well. So it really means a power. And the power is, well, it's the usual sort of power for a matrix. It's just C multiplying itself k times. So C to the kth power, this really is a power. But it also kind of serves as an index for our sequence as well. Now, when I put brackets around a matrix, that means I'm extracting the I and jth element. So bracket I subscript ij means the element in row I and column j. And this can be any row I and any column j. So basically we're saying all elements in absolute value. This could even be modulus, I guess, because we're using complex matrices and made the definition somewhat general. So modulus in this case, all elements in modulus are less than epsilon. So this is what we mean by a convergent matrix. It means as we multiply these things together, basically the matrix is tending towards 0, that object where all of the elements is equal to 0. Okay, so convergent matrix, multiply itself any number of times. If you keep doing that, go out to infinity, the thing is going to converge to 0. Now there's a theorem which is important, and this is a theorem which we state in our numerical analysis book, and that we want to use now. In fact, we really only want to use a couple of parts for it, but it's useful to have, and this concept is useful to have in general. So it is, or the equivalent statements are the following. C is a convergent matrix, and that is equivalent to the fact that if we have an induced matrix norm, or some induced matrix norm, if we take the limit as k goes to infinity of ck, remember ck is c multiplying itself k times, the limit of that norm goes to 0, or is equal to 0, which is equivalent to knowing that in all norms, the limit as k goes to infinity of ck is equal to 0. And this has to do with what we call norm equivalence. All norms in finite dimensions are equivalent. Those statements are equivalent to this following statement. The spectral radius of C is strictly less than 1. Okay, the spectral radius of a matrix C is defined as the maximum of all of the eigenvalues in modulus. So the maximum modulus of all eigenvalues possible. Now, my definition or my notation the for the spectrum of a matrix is this sigma c. Sigma c is the definition for a matrix. That's just the spectrum of a matrix. It means the set of all eigenvalues. So we're taking the maximum in modulus over the set of all eigenvalues, and that's what we call the spectral radius. So that should be less than 1 strictly. And then the final equivalence is that if we take the limit as k goes to infinity of ck against x, where x is any vector, then we should find the limit is 0. Okay, so all of these statements are equivalent. Now, it's mostly these two that we're going to be interested in using, but these ones are also quite useful to know. So knowing that a matrix is convergent is really knowing something about the smallness of this thing as after I multiply itself times itself a number of times. So knowing that a matrix is convergent is precisely equivalent to knowing that a number in absolute value or modulus is less than 1. And so what do I know about such numbers? This could be a number in the complex plane. And so if I multiply it by itself k times, that's the power, then that should approach 0. Okay, so it's entirely analogous to this idea, this concept, that if we have a number which is in modulus less than 1, and I take enough powers of it, it's going to tend towards 0. Okay, that's the concept of a convergent matrix. Now here's the general convergence theorem for these general linear iterative schemes. Suppose that A and B are invertible. Suppose that F is given, and suppose that U is the solution of A, U equals F. And this is just a simpler way of saying that. U is A inverse F. Then the general linear iterative scheme converges unconditionally if and only if the error transfer matrix for that scheme has a spectral radius which is strictly less than 1. So you probably remember this from Math 571 or your numerical analysis course as an undergraduate or whenever you took it. Of course, the error transfer matrix is defined in the usual way, I minus B times A. All right, so let's prove the forward direction. So what are we assuming in the forward direction? So we are going to assume first that the method converges unconditionally, and then try to show that that means that the spectral radius is less than 1 in modulus. Or, sorry, the spectral radius is strictly less than 1. We don't have to add the word modulus there because it's already an absolute value. Okay, so how do we do this? Start by assuming that our general linear iterative scheme, which is equation 2, converges for any starting value. Okay. And by the way, if it does converge for any starting value, the only possible thing that it can converge to is U. That's just an aside. That's because it's a linear iterative process. We can show that that means that where EK is the error with respect to UK. So remember, EK is defined as U minus UK. That's how it's defined. And we can easily show that this means that the limit as k goes to infinity of EK is equal to 0. Okay, regardless of where we start from. Now we have to switch a little bit to the complex field. And this is because even though T is a real matrix, its eigenvalues are not necessarily real. They could be complex. So suppose that we have an eigenpair. That means a pair of a complex number and a complex vector of length n. Actually, I should be a little more clear here. This is a complex number or complex vector that is not equal to the 0 vector. Remember, an eigenvector can never be equal to the 0 vector. That's a law of nature. So we have this pair of a complex number and a complex n vector. And it's an eigenpair of T, and we're going to assume that the norm, the infinity norm of W is equal to 1. We can use any norm we like, but let's use the infinity norm, and let's assume that W is normalized so that its norm in the infinity norm is 1. Now we're going to set E0 equal to W. Now, why are we allowed to do that? Well, we said that this method converges for any U0. So that's essentially like saying for any E0, this sequence converges to 0. So let's take our E0 to be W. Well, if this is true, we're going to use the eigenvector eigenvalue property. It's easy to show that EK is just equal to TK, and this means the power, T times itself K times E0 is just equal to lambda K times E0. Okay, so every time we apply T against its eigenvector, we produce another eigenvalue. But this is an eigenvector because we've set it to be so. And so every time I apply T, I'm going to spring forth a new eigenvalue. So I get lambda to the K in the end. So this is a complex number raised to the K power. And now I know that the limit as K goes to infinity of this guy is 0. And this guy has a fixed limit. E0 is just some fixed number. So what does that mean? That means that effectively lambda K has to go to 0. Or if you want to look at it this way, it's modulus, okay? Or lambda, or the modulus of lambda to the K power has to go to 0. All of those are equivalent. Well, the only way that this can happen is for lambda to be equal to 1. Okay? Or sorry, lambda to be less than 1, not equal to 1, less than 1 in modulus. That's the only way that that can happen. Now, we took an arbitrary eigenpair, all right? We took an arbitrary eigenpair, so what does that mean? That means that all eigenvalues have to satisfy the same property, that in modulus, they're strictly less than 1. So that means that the spectral radius is less than 1. So that's how we get from assuming convergence to proving that the spectral radius is strictly less than 1. Okay. Now, let's go the other way. Let's assume that rho is strictly less than 1. Then this should say not theorem 8, this should say the last theorem. By the last theorem, for any x, remember, for any x, the limit as k goes to infinity of tk times x is equal to 0. Right? Because that was this equivalence. So we're really using just the equivalence of these last two. That's all we need. All right, but what does that mean? If that's true, then that's just a restatement of unconditional convergence, because it's saying that, well, if I put any vector starting value, right, and that means any U0, so any starting value gives rise to an arbitrary, essentially, E0. And so this has to have limit 0, but that's just like saying if I follow this back using this little equality here, little easily proved equality, that the limit of EK is equal to 0. Okay. So that's what we mean by unconditional convergence. So that closes the loop and that proves the result. Any questions about that? It's a standard result that you guys have seen in 571 or whatever course you took on numerical analysis. The next thing we want to establish is something which is a little bit more easily computed than the spectral radius, because the spectral radius requires knowing eigenvalues. If you remember what we talked about in 571 or your numerical analysis course, computing eigenvalues is not simple. Of course, you can imagine that they can be computed theoretically any way you want, but computing eigenvalues practically isn't simple. However, taking something like a norm is easy to do. So that's what we're going to do. We're going to come up with a criterion which is easily checked, like the size of the norm. So if the norm of t is strictly less than 1, for any induced matrix norm, where T is the error transfer matrix, then the general iterative scheme converges for any starting point. Furthermore, we have the following error estimates. So let's at least do this one. This one actually is very easy. This one's a little bit harder. So an error estimate just says, well, all right, the size of this guy here really dictates how fast I'm converging to zero. Or it's not a tight bound necessarily, but it's some error estimation procedure. It turns out it is actually a pretty good bound. It's pretty tight. So we're going to use the following well-known fact that for any induced matrix norms, so you remember what an induced matrix norm is. It's the same as that thing called the operator norm. So if you're used to thinking about something called the operator norm from functional analysis, it's the same. So for any induced matrix norm, the spectral radius is always less than or equal to the value of the norm, okay, of T. The spectral radius of T is less than the norm of T, as long as the norm is an induced matrix norm. So this means that if this is a sufficient condition, not a necessary condition, if we know that the norm is strictly less than 1, then just using this basic inequality, clearly the spectral radius must be strictly less than 1. So we can use the last theorem to generate that desired convergence result straightforwardly, because that was an if and only if. So we have convergence if you can find a norm and show that that norm, or in that norm, T is strictly less than 1. Then you get convergence. Now, what about the error estimate? The first one's quite easy. The first one, remember, we have this kind of fundamental little equality. EK is equal to TK E0. Very easy to prove. So if you don't see it right away, sit down with a little piece of paper. This goes from the general result, or the general definition, which says that EK is equal to T times EK minus 1. Now, so let's just use this property here. So that means the norm of EK is equal to the norm of this vector, TK E0. And now we're going to use something called consistency. You guys remember consistency from numerical analysis? I kind of try to hammer it into your skulls, right? So over and over again, consistency, submultiplicativity, and sometimes you wake up in the middle of the night with a nightmare and you scream out consistency, submultiplicativity, right? So you remember it. That's the property we're using here. And the property we're going to use here is submultiplicativity. We're multiplying T times itself K times. So we take the norm of that. T is a square matrix. Then we find that this one just uses this following property here. So if I have two square matrices and I take their induced norms, then the norm of the product is less than the product of the norms, less than or equal to. So that's called submultiplicativity, and that's what produces that estimate there. And now you just replace the error vectors with how they're defined to get the error estimate exactly as it was stated on paper. So there's the error at level K, that's iteration level K, and this is the error at the initial time, or the initial step. And so that's the error estimate we wanted. So if T is less than 1 norm, then of course this number is going to go to 0. And that's kind of stating what we call a linear convergence rate. A linear convergence rate. Now let's try to figure out how to do the second error estimate, and put this one in your pocket because we might need that one. Okay? So keep in mind that estimate. Let's see if we can use that one in some way, shape, or form to derive the second estimate that we want, which is a little bit more complicated. Well, let's kind of break down that second estimate for just a second before we get into it. What's different about this one? Well, this one says that the error at iteration level K is less than something. Okay, we'll look at that in a moment. times the error that you measure between the first two iterates, between the initial error and the first error that you generate. Sorry, I got that wrong. Between the first iterate and the, let me say that again, the 0th iterate and the first iterate, not the errors. So this isn't really what we call the error. This is an error. This is not the error, but it's an approximation of the error. Turns out it's a pretty good approximation. If I measure the difference between two iterates, that can give me a good handle on what the error is doing. So it's the difference between the first two computed iterates times this thing. Now, this thing down here, we're safe because t is strictly less than 1 in norm. So this number here is like 1 minus 0.9, right? Think about this being like 0.9, 1 minus 0.9. We're not dividing by 0, so we wipe our brows and move on. So that's not 0 on the bottom. It's some positive number less than 1. And this number is going to go to 0 because, or this sequence is going to go to 0 because of this assumption. Okay, so that's the breakdown of the estimate. Let's see if I can stop talking and start proving this. All right, so E0, let's think about how E0 is defined. E0 is U minus U0 by definition. Let's add and subtract U1. So if I add and subtract U1 and use the triangle inequality for norms, remember this is any vector norm that I want to use, any vector norm at all. Well, use a triangle inequality. This just gives U minus U1. That's called E1. So that's E1. And U1 minus U0, that's the thing that we think is going to appear in the right-hand side. So let's just put that off to the side for a second. Now, what about U minus U1? That's E1, as I said. And that's equal to T times E0. And T times E0 can be written in a slightly different fashion as T times U minus U0. That's exactly equivalent. So now let's take the norm of this thing we see here. So the thing we see there gets a norm like this. So it's U minus U1 in norm. We're using this equivalence here. And we're going to use the consistency. So consistency of norms. Remember, I didn't say what that means. So consistency of norms means that if we have something like a matrix times a vector, that's equal to or less than or equal to the induced norm of t times the vector norm of y. So that's what we call consistency. So we use consistency. And then we're going to sub back in that this is just E0. Okay, so that comes right from that. So we're going to sub that in right there, ultimately. Okay, so let's write it out. We have E0 putting in the same trick we had last time, adding and subtracting 1, that gives E1. U1 minus U0, that just stays around. And of course, this one and the last step we showed is less than that. Okay, so now we can throw this guy over to join his friend over there on the left-hand side. So if we do that, this comes over with a minus sign. And then we can divide through by that. We can use the distributive property, take out a common factor, and then divide both sides by that common factor. And the common factor here is this guy. So that's what we're dividing both sides by, 1 minus norm of t. Now let's go back to the first estimate. The first estimate, we had this guy appearing, right? That's E0. So now we have an estimate for E0 involving all this stuff, and so we can throw it back in there. So there's my first estimate, just restated, okay, or there. And now I'm going to replace this with this estimate that I generated up here, falls into there, and that's the desired second estimate. Now, why did I go through all this trouble, and why is that estimate useful? It's because what we can do is it doesn't require a bunch of computations. It gives us a nice understanding of what or how this thing is going to 0. So presumably we know how to calculate the norm of t. Okay, and we find out that's less than 1. Let's say we use the 2 norm. Now, we don't know the first error. So this estimate here, you have to ask yourself, is this practical? The only way that that could be practical is if you knew what U was, then you could compute it. You could say, if I know what U is, I can compute U minus U naught, take the norm, so you can compute the error. Okay, the norm of that error we can also call the error. So that's not computable. However, this object down here is computable, as is this part and that part. No problem computing all of that stuff. So this gives us a computable error estimate. Okay. And so sometimes the theoretical is great. In fact, it's what we use to prove this guy, but it might not be computable. Theoretical is good, but it might not be computable. We can transform it into something which is computable, and that's what we get. Okay, so that's how you prove the second from the first. Part 2 of this chapter 1, which is classical or iterative methods. And you can see, oh man, this is like the big green monster here. This section on splitting methods is what we're going into next time. Has like 45 slides, but we couldn't help ourselves. We just like creating slides. Well, what we're going to talk about in this section of splitting methods are kind of the big three. But I want to talk not just about the big three, but also about some variants. So the big three are Jacobi, Gauss-Seidel, and Richardson. All right, so the big three are there. But I'm also going to discuss in this, I'm going to discuss two different flavors of the Gauss-Seidel method, the forward Gauss-Seidel, and also something that you may not have seen before called the backward Gauss-Seidel. And by the way, before I forget, let me put on my do not disturb. There we go. Okay. But I'm going to talk about variations of Gauss-Seidel forward and backward. And Jacobi, I'm going to talk about a variation of this called the weighted Jacobi method. I could also talk about the weighted Gauss-Seidel method, the forward, backward, weighted Gauss-Seidel methods. And so I can generalize that a bit as well. And then the last one we're going to talk about is Richardson's method. And I don't really know a way to modify Richardson's method without making it just Richardson's method again. So those are the three. All right, so let's first talk about the classical splitting methods. Jacobi and Gauss-Seidel are splitting methods. Actually, Richardson's method is also a splitting method, but the first two differ from Richardson's in that they are defined by what we call the diagonal splitting. And so I don't know if you've ever split logs before, but if you split a log, you take a sharp axe and you hit a log and it splits down the middle, right? Or if you hit it in the middle. So these diagonal splitting methods are kind of the same. So it's a little bit like the axe coming here and splitting that matrix into a lower triangular part and an upper triangular part. So that's why I call it diagonal splitting method. So we think about A as being composed of three parts, three matrices, a strictly lower triangular part, a strictly upper triangular part, and a strictly diagonal part. And I'm going to choose to use the notation from classical splitting methods. And that is, instead of writing the upper triangular part as a U, we're going to write the upper triangular part as minus U. Okay. Now, the reason why we do this is historical. It's because we usually take that minus U and throw it onto the right-hand side where it acquires a plus sign. And so this is a minor annoyance, and it's an annoyance to me because it differs from what I wrote in my textbook on numerical analysis, but it's a minor annoyance. Okay, so just keep that in mind. The strictly upper triangular part is designated as minus U, the matrix minus U. Strictly lower, minus L, and the diagonal part, thankfully, is not minus D, but just D. So Jacobi and Gauss-Seidel are based on this canonical splitting diagram. All right, so let A be given. Consider A equals D minus L minus U, where D is the diagonal part of A, minus L is the strictly lower triangular part. That means it doesn't get anything on the diagonal part, it just puts zeros there, and it puts zeros on the diagonal and above the diagonal. Okay. And the strictly upper triangular part of A is what we call minus the variable minus U. So that one in the lower triangular part and on the diagonal has just zeros. So this decomposition, which was illustrated in the previous figure, is what we call the canonical splitting or diagonal splitting of A. Okay. I'm not sure if I had to make a definition about that, but okay, there it is. I like to make definition about everything. You guys know that about me now. There's another picture of it. And thankfully, I have an example. All right, so here's our example matrix A. It's a 5 by 5 matrix with essentially random entries. In fact, I did generate this randomly using MATLAB. So the diagonal would just be a matrix that has all zeros except on its diagonal. It's just going to have the numbers 10, 9, 9, minus 7, and 7. 10, 9, 9, minus 7, 7. Now, what about U? U is defined at in the way. So U is defined such that it minus U is the strictly upper triangular part of A. So let's take the strictly upper triangular part of A, and we're going to throw that into a matrix. But in defining U, we're going to switch all the signs from minus to plus and plus to minus. All right, so that's exactly what I've done here. Notice that U has nothing on its diagonal, nothing below the diagonal, and above the diagonal, you take the elements that you saw there in A and you flip the sign. And hopefully I did this correctly. Every minus that you see up here, for example, minus 8 becomes an 8 here. And analogously with the lower triangular matrix. Minus L is defined as the strictly lower triangular part of A. So L is the lower triangular part of A, but changing the signs. And the only one that had a sign which was negative up here is minus 8. So minus 8 becomes a positive 8, and all the rest of them positive changes to negative. Okay, so that's what I mean when I say a canonical diagonal splitting. Canonical splitting, diagonal splitting, same thing. So notice that one thing I want to bring up based on this canonical splitting is that if A is an SPD matrix, remember what SPD means? So it's symmetric and has this positivity property, then we can easily show that this means that the diagonal entries have only positive entries. The diagonal matrix or the diagonal entries of A are only positive. And so that's one thing that follows from, it's an easy proof, not too bad, from the assumption that A is SPD. The other one is, this one's even simpler, and we can see that the strictly upper triangular part is equal to the transpose of the strictly lower triangular part. This is just because of symmetry. All right, so two basic facts that you get from splittings. Now we are going to be dealing with coefficient matrices. Remember the problem that we're trying to solve here. So the problem that we're trying to solve is always A times U equals F. Okay, so A is the coefficient matrix, and F is the forcing term or forcing vector, which is given, and U is the vector of unknowns. So we're going to be dealing in a lot of cases where this coefficient matrix A is symmetric, positive, definite. In some cases, we'll look at matrices where it's strictly diagonally dominant, or maybe just symmetric and invertible. But in any case, it's going to be a very important class of matrices for us that A is symmetric, positive, definite. All right, let's first define the Jacobi iteration method. And so here you'll see why we like to take those minus signs in this canonical splitting. So suppose that A has a canonical splitting, and let's assume that D is invertible. And we will see why D needs to be invertible in a moment. Then the linear system AU equals F can be written entirely equivalently like this. D times U equals U plus L times U. Okay, that's entirely equivalent. Now, how do we define Jacobi's method? Where does it come from? It comes from looking at this equation, just staring at it for a little bit and saying, like thinking like if you're a cave person, like how would I find out what the true solution is? Well, maybe you don't know how to find the true solution, but you do know how to iterate things. So let's do that. Let's switch this U to a UK, and let's switch this U to UK plus one. All right. Now, why do we do this? And is it useful? And is there any consistency built into this idea? Well, okay, so let's first think about a consistency statement. If I switch this to UK plus one and this one to UK, let's first make sure that if we had a fixed point, and what a fixed point means is that UK and UK plus one and all the UKs are equal to the true solution, okay? Or just some fixed number. So suppose that UK is just equal to some W vector. Put that back in. So what do we see? Well, if that happens, no, we don't want to do that. I don't want to do that. I really do want to say, suppose that UK is equal to the true solution. A inverse times F. What if I put the true solution in? So what do I get? Well, if I put the true solution in, then I really have this on the right-hand side, right? But this says for the true solution, what you get on the left-hand side is D times U. In this iteration process is saying oh no, you don't get du, you get duk plus one. But d is invertible. So that means that actually uk plus one must be equal to the true solution. So the true solution is a fixed point for this iteration process. Okay, if I throw in the true solution, then I get the next operation is just going to be the solution back. Okay, or in other words, I'm always going to be equal to the true solution. That's what we mean by a fixed point. All right, so the first thing we want to ensure if we write something down like this is that we're not messing up fixed points, and the fixed point should only be equal to the true solution. Well, check. Okay, that all makes sense. Now, what is it about this that is kind of nice? Well, to solve this problem, I don't have to solve anything as hard as the original problem. Remember, the original problem is A times U equals F. This is a lot simpler to solve because I only have to invert a diagonal matrix to solve this problem. And we already know how to invert diagonal matrices. As long as all the diagonal entries are non-zero, I can invert this just by inverting the diagonal entries individually. So I know how to calculate the inverse for this is trivial. And so really what I could do is I could write for this guy, I could say this iteration process is entirely equivalent to saying UK plus 1 is equal to D inverse U plus L. And again, the reason why I'm using minus U and minus L in the canonical splitting is so that these don't have, there's no minus signs here. UK plus D inverse times F. Okay, so it's very simple to go from the K level to K plus one. I just do this solve here. So this is what we call an explicit scheme. It's explicitly solvable for the next iteration. We don't have to invert a system or anything very complicated like that. So this is what we call the Jacobi iterative method right here. So the question is, can this be written as a general linear iterative scheme? Well, the answer is yes. It is a general linear iterative scheme. What do we need to identify in order to make it so or to deem it so? Well, what we would need to identify is B, or we need to say what is B in this case. All right, so that's the next little easy thing to work out. So for the Jacobi method, it turns out the iterator matrix B is just equal to D inverse. Okay, I don't think I worked that out there, but you can work it out easily. I'm going to leave that as an exercise. Very easy to show that the Jacobi method is just a general linear iterative scheme where the iterator matrix is just equal to D inverse. Okay. So remember what the structure of a general linear iterative scheme is. It says it has to be of the form UK plus 1 equals UK plus B times F minus A times UK. So we have to take what we had on the previous page, do some manipulations, and work out that, this must be D inverse. And I claim that that's easy enough to do. So do that little exercise. You'll find that it's just a general linear iterative scheme where B is equal to D inverse. And so I can just define Jacobi method as a general linear iterative scheme where B is equal to D inverse. That's an equivalent way of doing it. And if that's true, then the error transfer matrix is just equal to I minus, by definition, it's I minus B times A, but B is equal to D inverse in this case. So the error transfer matrix is I minus D inverse times A. And so the iteration sequence is precisely just this. And in this case, I'm just rewriting what I know. B is equal to D inverse. So it is a general linear iterative scheme. Okay, that's the Jacobi method. Now we can do some manipulations on that error transfer matrix. Error transfer matrix is given here, and we can write it. You can write it 10 different ways, actually. Let's write it in just one other way. So the one other way I want to write it is, let's replace the identity with D inverse times D. And so there's the identity, minus B times A, but B is equal to D inverse. I'm going to use a distributive property to pull out this common factor here. And so what I get is, using distributive property, D inverse times D minus A, but A is just equal to minus D. Sorry, A is equal to D minus U minus L, but minus A is equal to minus D plus U plus L. So the D's cancel. And lo and behold, we see that another way of writing the iterator matrix is this way: D inverse U plus L. Now in component form, the Jacobi method can be written exactly as follows. So here's how you define this. So this is the complicated looking component form, but this is actually how we do this in a computer, how we code this up. But let me show you how this is gotten, how this is arrived at. So we just start with a, no, that's not what I want to start with at all, is it? You want to start with the iteration scheme, but I'm going to start with the iteration scheme in a slightly different way. So I'm going to do minus L UK plus D UK plus 1 plus U, capital U, UK equals F. So that's an entirely equivalent way of writing the Jacobi method. But now I can think about this as being a portion of the A matrix, is the lower triangular portion. So when I remember how I do matrix vector multiplication. So if I have a matrix times a vector, and that's equal to a vector. So what I do is I take a row out of the matrix A, I multiply it times the vector, and that gives me the entries of this vector, right? So I take this row out times that to get that one, and then this one might get times this gives me this one, and finally this one times that gives me that. All right, but what I'm doing is I have to think about, as I go down here, I have minus L and minus U up here, and then D on the diagonal. Okay, so this is expressed like that. I'm already breaking up A into its lower triangular portion, diagonal, and upper triangular portion, times this kind of mixed vector where I have part of it's UK, part of it is UK plus 1, and part of it is UK again. So what I'm going to do is I'm going to imagine, well, what does this look like for if I set this equal, if I just pick out the ith component. But pick out the ith component, then this portion here, and then move it to this other side, is going to be equal to this portion right here. That's just essentially that L times UK. And what about this guy? I have the sign wrong on this one. This should be a minus sign. What about that portion there? Well, when I take that to the other side, that just becomes this portion here. Okay, so this is the upper triangular part of A. It's sort of like this part times that unknown vector or that previous vector UK. But if I break it into component form, that's what I get. Now I leave this diagonal portion over on the other side. So this is basically like the diagonal element, and the diagonal element is going to be AII. But then I realize the diagonal is not 0. I can divide by that. So I'm going to move the diagonal element that sat here down to here. All right. So this is how I figure or compute the Jacobi method in component form. So let's also think about, so this might take a little bit of time for you to think about it on paper. How do I compute the Jacobi method in component form? And component form is really how we do everything in the computer. You have to do one component at a time. You can't do one vector at a time. Well, actually, you can in modern computers. That's called vectorization. But really, vectorization really needs to understand how components are working. But notice what happens in this form. What I do is it doesn't matter what order I update the components. It doesn't matter if I do I equals 3 first, or I equals 10 first, or I equals 1 first, or I equals 100 first. It doesn't matter. There's no real order that's specified or desirous when I'm computing the components of the Jacobi method. I can do them in any order, and that's an important point that we're going to take advantage of later on. It may not be obvious from what I've just said, but what you can do is do a little small size computational example and convince yourself that the order isn't really important. Now that differs from from what we'll find with the Gauss-Seidel methods. Okay, so either the forward or the backward. It turns out the order in which I do that update is very important. In fact, it can only really be done in one way. So we'll get to that in a moment. Now, let's prove that the Jacobi method is convergent. And let's start off with I wouldn't call it an easy proof, but one which is familiar to those who took numerical analysis recently. And it's proving this, the Jacobi method is convergent for what we call diagonally dominant matrices, or row-wise diagonally dominant. So what do I mean by a matrix which is row-wise diagonally dominant? Well, it's one where for each row I, the diagonal element in that row, in modulus or absolute value, we're in real land, so this is absolute value, is strictly greater than the sum of all of the other off-diagonal elements in that row in modulus. So take all the elements in that row, not the diagonal element, take the moduli or absolute values, sum them up, and that number is going to be a number which is greater than or equal to 0. And it's going to be, or must be, strictly less than the absolute value of the diagonal element. This is what we mean by a diagonal dominance. Well, there are a couple of things that you can prove right away for diagonally dominant matrices. Well, first of all, the diagonal elements must be numbers which are not equal to 0. They can't be, none of the diagonal elements of a diagonally dominant matrix can be 0. The other thing you can show is that for any diagonally dominant matrix, they must be invertible. Okay, so if A is diagonally dominant, then it's invertible, and none of its diagonal elements is 0. So this is a common homework problem that I give in numerical analysis. You probably remember that. But what we can do then is show that if A is diagonally dominant, then the Jacobi method is well-defined. And it's well-defined because, well, what did we need for the Jacobi method to be well-defined? We needed the diagonal matrix to be invertible. And that's what we'll find here. And it's unconditionally convergent. So let's see how this proof goes. You probably remember the details of it. So if you want to shut off your brain, that's fine, no problem. You've all seen this before. And some of you could prove it much better than I at this moment. So let's suppose that we're going to use the infinity norm, because when we deal with diagonal dominance, infinity norm is the norm of choice. When you use a when you assume that the matrix is positive definite, then oftentimes it's the 2 norm which is important. And sometimes other, what quote unquote energy or spectral type norms are more important. So here it's diagonal dominance, so we use the infinity norm. So let's try to show, using our little theorem, our little corollary maybe, that we try to show that the error transfer matrix in the infinity norm is strictly less than 1. And if that happens, then we have convergence. So everything now is just geared towards showing that this is true. So since A is diagonally dominant, its diagonal elements are all non-zero. I already said that. And so that means that the method is well defined because D is invertible. Now we're going to compute what the error transfer matrix looks like. By definition, error transfer matrix is I minus B times A. Okay, we know that B is equal to the inverse of D. So that's the inverse of D right there. It's just the inverse of all the or it's a diagonal matrix where we take the reciprocals of the diagonal elements of A. So I minus D inverse times A. And so what is easy enough to show is that basically for the diagonal elements, we're gonna get 0. So if when I take this guy times this column, for example, these rows, so it transforms this by switching this to a 1. Okay, remember, a diagonal elements scales rows or columns according to whether you multiply it on the left or the right. And so in this case, this guy is going to scale, okay, this guy here is going to scale that row, and the next diagonal element is going to scale row 2. So multiplying the diagonal matrix on, or from the left side, is going to scale the rows. Okay, but in any case, what I get here is that for this row, that element is going to be 1, and all the rest of the elements in the row are going to be scaled by AII, or A11 in this case. But now we also have a minus sign there. So that's why I can say that I can say exactly what the elements of this matrix are. It's just going to have zeros in the diagonal, and the off-diagonal elements are going to be the same as the off-diagonal elements of A, but with a minus sign, and then scaled by the diagonal element from that matrix, from that row. Okay, so that's what the T matrix looks like. So now let's take the infinity norm of the T matrix, and all the rest of the computations are basically trying to show that in the infinity norm, this guy is strictly less than 1. Well, what is the infinity norm of any matrix? It's the maximal absolute row sum. The maximal absolute row sum. So what I do is I'm going to take the max over, this is wrong here. This is a typo. So this should be max between 1 and n. That should be an n. Okay, so that's the maximum row sum part. And then these are what we call row sums, okay, or absolute row sums. It's not hard to show that except for the 0 element, or the diagonal element, which is the one where j is equal to I, then the off-diagonal elements are going to have components like that. And so when we sum them up, we're summing components like that. All right, now since A is diagonally dominant, there's some delta, positive delta, such that the diagonal element in absolute value is greater than or equal to the sum of the absolute off-diagonal elements plus that delta, okay, for each I between 1 and n. And so this delta is independent of I. And therefore, it's not hard to show that this sum here, this is the sum that we have over here. This is the thing we have to show each one of these guys is less than 1 strictly. And so the way we do that is it's not hard to show that this number is less than 1 minus delta over alpha. Delta is the number that I introduced over here. And alpha is just equal to the maximum of the absolute, or the maximum absolute value of the diagonal entries. Now, if we get something like this, and both of these numbers turn out to be strictly positive, and of course, this whole thing has to be greater than 0. So what I would worry about, and on one hand, is if I subtract something from 1, I don't want to get negative, right? But we're fine there, no problem. Okay, so I'll leave it up to you to show this little part here. And if I can show that, well, this number has to be, I'm taking 1 and subtracting something positive from it, right? So this number here has to be strictly less than 1. All right. So that's how we show that in the infinity norm, the error transfer matrix is strictly less than 1. So this means by our theorem, or our, I guess it was a corollary, we know that the method has to converge. Okay. Now, what if we had used some norm and we find, oh, well, the norm is not strictly less than 1. Do we know that it diverges? Would we know that it diverges? The answer is no, because we're only using a sufficient condition here, not a necessary condition. So it is possible that we chose the wrong norm, and you find that in that norm, the error transfer matrix is just slightly bigger than 1. But that doesn't mean it doesn't converge. That just means you have no information because you're using a sufficient condition test. So this is sufficient for convergence. We've proven convergence. Now, one method that we're going to run into, which turns out to be really important, is something called the weighted Jacobi method. And the weighted Jacobi method is exactly like the original Jacobi method. Okay, so there's the original Jacobi method. And normally this would be a UK plus 1, except that you're going to compute that next iterate, but you're not going to call it UK plus 1. You're going to put it in your pocket, and then you're going to do what's called a weighting step. So the weighted Jacobi method, you use this weighting parameter where W is some number between 0 and 1. And in fact, actually, this number can go all the way up to 2 if we wanted to. So this is called the weight parameter, omega. And so to compute UK plus 1, we're going to weight the new thing that we just computed against the old thing in what's called a convex combination. Now let's think about a limiting case. Suppose that omega was equal to 1. What happens when omega is equal to 1? Well, then this just becomes 1 times z, and this is 0. So this is just good old-fashioned Jacobi. So omega equals 1, that's just Jacobi. But omega strictly less than 1, between 1 and 0, that's where something more interesting happens. This gives you the weighted Jacobi method. So is a weighted Jacobi method useful? Does it converge? Blah, 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 all these things. Well, it depends on the matrix you're using. And it turns out for us, this weighted Jacobi method is going to be quite important. It's going to be quite useful for developing what we call multigrid methods. So let's put this in our back pocket and not worry about it now, but we'll come back to that. But here are a couple of questions. So first one is, what is, can't spell what is the error transfer matrix, or the iterator matrix for weighted Jacobi? So what's that? And then the next question is, well, what if I know that, then what is T? How do I compute the error transfer matrix for weighted Jacobi? So this one is the iterator. Of course, once I know the iterator, then I know the error transfer matrix. But so that's a question for you, maybe a little homework exercise. What is the weighted Jacobi iterator? Okay, put that in your back pocket for now. We'll come back to that. Oh, no, I lied. I lied. I'm stating it here. Here's what the answer is. Sorry. I forgot what I wrote. So the iterator, sorry, for the weighted Jacobi method is just omega times d inverse. And so that tells us immediately what is the error transfer matrix for that. It's just I minus b times a, but b is equal to omega d inverse. So I apologize, I forgot. So I give you the answer there, but it still is an exercise, so go do the exercise. How do you show this? All right, Gauss-Seidel method, how do I define that? It's similar, it's defined along similar lines. So what I do is, let's start off with our canonical splitting. Okay, D minus L minus U. And so remember what we start with. We have our original matrix, A, U equals F. So this can be written as minus, usually write L first, LU, plus du plus uu. And so that's equal to f. So then I'm going to take these guys here, and I keep making the same mistake. So this is just minus. So then I take these two guys, or no, just the one. Just take this guy and move it over here with this friend f. And so I immediately get this. And now we're going to do the same thing we did before. We're going to replace the u on this side with uk, and the u on this side is going to be replaced with uk plus 1. Now, it doesn't look like this is as nice as Jacobi, but it has some additional nice properties that Jacobi doesn't have, which we'll get to in a moment. But now, what do we have to assume in order to make this a practical method or a well-defined method? Well, we have to be able to invert this guy to get that out of there so we can explicitly figure out what uk plus 1 is. So let's assume that d minus L is invertible. But what do we need for d minus L to be invertible? It's a triangular matrix, right? In fact, it's lower triangular matrix. What do we need for that to be invertible? We need D to be invertible, or non-zero diagonal entries, and that's enough. So if D is invertible, then D minus L is invertible, and so then we can do the following manipulations. So we start, this is our defined Gauss-Seidel method. So first invert that, we get that, right? Just applying the inverse. So I'm going to show you how you compute the iterator matrix in this case. So now I'm going to add and subtract the u vector. Add and subtract u vector. So I'm going to add uk vector. I'm going to subtract it off right here. So how do I know that that's just uk? Well, d minus L inverse times d minus L, that's the identity. So this whole thing here is really just uk. But now I have a bunch of other matrices here, right, in the same pattern. So I can use the distributive property to pull out that d minus L inverse. So if I use distributive property to pull out d minus L inverse, then I can show that everything else in the parentheses collapses to the following: f minus a times u. F minus a times u. So do it. Do that little exercise. See if you can show that whenever I use the distributive property to pull out these factors, these common factors, then what's left over in the interior is just f minus a times u. So this tells me that this is a GLIS, a general linear iterative scheme, and the iterator matrix is d minus L inverse. That tells me all that information. So that's how I can define this thing called the Gauss-Seidel method. In fact, this Gauss-Seidel method in multigrid literature and multigrid terminology is actually a special form of the Gauss-Seidel method called the forward Gauss-Seidel method. Forward Gauss-Seidel. And that, of course, is going to contrast with something we call the backward Gauss-Seidel method, which we'll get to in a moment. But in any case, I can define it just by telling you what is the iterator matrix for that. It's just D minus L inverse. And the error transfer matrix is, of course, just always I minus B times A. But since we know what B is, we can put it in, and that gives us an explicit expression for the error transfer matrix T in terms of the components of A. And then, of course, the iteration, the general linear iterative scheme is just defined as normally, only here we're replacing B with what we know it to be. That's called the forward Gauss-Seidel method. As before, we can transform the error transfer matrix into another form. So there it is by definition, but we can do some manipulations on it. Let's transform this I identity matrix to this form of the identity, D minus L inverse times D minus L. Pull out this common factor. Here we're going to rewrite A as D minus L minus U. And if we pull out that common factor, then we have a big parentheses full of stuff, and the stuff just collapses down to U. So we get D minus L inverse times U. And so notice all the letters in the alphabet or in the alphabet of the canonical decomposition of U or A appear. D, L, and U. All right, so that's another way of writing the error transfer matrix for the Gauss-Seidel. You've probably seen that before. What about the component form for the Gauss-Seidel? So let's start off by writing things the way we did before. So the Gauss-Seidel method, what we did was we attached to this D minus L factor, we attached the UK plus 1. Previously, we had moved this guy to the other side. We're going to bring it back over with its brothers or sisters, and we're going to recognize that this one is attached to the UK. So what does this look like? Well, if we break this into, again, row multiplications times some vector equals components of F, then what we get are things which look like this, okay? We take a row out of A and we multiply it times this weird vector, which is partly K plus 1 and partly K, and set it equal to F. All right, now this one, this update should be done in a certain fashion, right? This update should be done in a certain fashion, as I'm going to show you in just a second. It might not be clear by looking at this, but this really begs to be done in a certain way. Okay? We're going to use what's called forward substitution. Forward substitution, right? So basically, we're going to use this and think about, let's do I equals 1 first and see what we get. Well, if we do I equals 1 first, then we get just this. Okay, just put all the numbers in there for here. If we put in I equals 1, then the only term that's going to be here is A11. All right. And what goes here is going to be everything else. Okay. So there's A11 times U1. And that's just this term here, except I've thrown the A11 to the other side. Okay. But there's only one unknown term, and that's just the one having to do with I equals 1, just U1, K plus 1. So I can explicitly solve for that. There's no K plus 1 over here on this side at all. Okay, that's great. So I've got that first component. Now let's move on and go to I equals 2. Well, if I equals 2, remember we already know U1. So we immediately use that in the calculation in the update. This is where we differ from the Jacobi method, because the Jacobi method would have this still be K. So Jacobi method, that's why they say Jacobi method does not use new information in the update, whereas Gauss-Seidel uses new information. All right, so we immediately use that one that we found there, it goes in there. And we compute U2, the update. Let's go on to U3. Now we know U1 and U2. We now can compute U3 because we're going to use U1 and U2 in this thing. To get that formula, I just modified this formula just by looking at it. All right, so I'm going to use U1 and U2 here. I have to use, remember now I'm working with row 3 of A, the coefficient matrix. Yep, so I'm using 1 and 2. That's there. And these guys here are still the previous guys. So those are known to me because I computed them previously, and I can get U3. And now I can do U4 and U5 and so on, all the way up to I equals N. All right. I can do I equals 4 to I equals N minus 1 in exactly this fashion. But when I get to I equals N, I'll see that I've run out of these old components. They don't appear anymore. There's nothing there for old components. I'm using only all the new components that I just found, and I can compute the nth one. So this one, it begs an ordering of this process for updates. So Gauss-Seidel has to be updated in a certain order. And this order we call the forward sweep. So you start at I equals 1 and you go to I equals N. And that constitutes doing this forward sweep by plugging into this generic formula. It's just that you have to look at this formula and say, there's an order of the update, and that order is important. Okay? So there's my general formula for the update for Gauss-Seidel, but it has to be done in the forward order. All right, we can prove just like we did, and I'm not going to go through the gory details of this. We can prove just like we did for the Jacobi method that if A is diagonally dominant, then the forward Gauss-Seidel method is well-defined and the method is convergent. And the technique that we use to do this proof is we want to show that the error transfer matrix in the infinity norm is strictly less than 1. All right. So you've seen me go through this proof in 571, numerical analysis 1. And so it's the same details, more or less, and I hope they're all correct. Please do have a look at the book. I really want to know where the errors are so we can go in and fix them. But that proof should be more or less the same as what you'll find in the book. It's just long and tedious. Now, this brings us to something called the backward Gauss-Seidel method. So the backward Gauss-Seidel method is like the forward, except that we start by saying, okay, we have LU plus DU, don't do that again, minus UU equals F. And remember what we did with regular Gauss-Seidel. We put a K plus 1 here and a K plus 1 here, and we put a K here and moved that to the other side. So backward Gauss-Seidel, we're going to do the opposite, and we're going to put a K here, K plus 1 here, and K plus 1 here. And that's how you get the backward Gauss-Seidel. All right, so you can do the solution procedure. And so previously, or in other words, the conversion procedure to see that it's a GLIS method. And it precisely is. The only difference is every time you saw L in the forward Gauss-Seidel, you just replace that with a U and vice versa. Just swap the two roles. Okay, and otherwise it's exactly the same. So the B matrix is the iterator. That's D minus U inverse instead of D minus L inverse. The error transfer matrix is given once you know the iterator and so on and so forth. So the iteration scheme is precisely this. And the only difference here is that instead of what we had for the forward Gauss-Seidel, we have D minus U instead of D minus L. Okay, and then you can do a manipulation to find another expression for the error transfer matrix, similar to what we did for the forward Gauss-Seidel. And of course, you can go through more or less exactly the same proof and show that the backward Gauss-Seidel is convergent as long as A is diagonally dominant. And I'm going to give you another way of proving this in a moment. Well, not in a moment, in a few class periods. Now, I want to go through this and take just one more minute of your time. I'm going to talk about how do we do the component form of the backward Gauss-Seidel. And you might, as you might expect, we use forward substitution to compute the Gauss-Seidel. For backward method, we're going to use back substitution to do the computation. And all we do is we change our outlook of the structure of this. So the structure is exactly swapped as from before. Okay, it's whereas forward Gauss-Seidel we had one structure, for backward Gauss-Seidel we now have that. That translates into this component form. And so we notice here that the updated components tend to be on the back end. They tend to be on the back end. So that means what we're going to do is we're going to start with I equals n, and we're going to go in reverse order. So start with I equals n, and we can solve for un first using only old stuff. And then we can proceed on to I equals n minus 1. We're going in reverse order. And now we're going to use that new thing that we just updated from here. And we're going to use all the old objects or all the old pieces from the K level step to compute this one at n minus 1 and keep going. Now you go to n minus 2. So for n minus 2, you're going to use n minus 1 and n. I guess that's n minus 1 and n in this update. We're going to use those as the new pieces that we found in these two steps, and then all the previous pieces. And then you go proceed all the way until you get to I equals 1. Okay, I equals 1. And by the time you get to I equals 1, you're only using all the new updated information to get that update. Okay, the K plus 1 level stuff. And so the component form of the backward Euler method is, well, not exactly. It's nearly the same as the forward Euler, except that I have to go in backwards order or reverse order. And this backward order is what we call a backward sweep. That's in the multigrid terminology. It's called a backward sweep of the grid to get this. All right, so that's where I'm going to end for today. Next time we're going to pick up talking about Richardson's method. You can see we really did get bogged down in that lengthy splitting part. Richardson's method is the last one that we're going to look at. It's a splitting method. It's not based on canonical splittings or diagonal splittings, the same as the previous two. It's a little bit different. And of course, the main thing about the Richardson method that you probably remember again in your nightmares is this diagram and how you find the optimal value of the splitting parameter, etc. We'll get to all that next time. And so I will stop there. And you guys have any questions? So if not, if you think of one later on, you can always email me, and I'll stay on the line also for a few minutes if anyone wants to stay on and answer any questions in person. But otherwise, I'll see you guys on Tuesday, right? All right.